In this video, we're going to talk about some box-on-box problems. Let's start with this one. A 400 kilogram box is on the back of a 2,000 kilogram truck. The coefficient of static friction between the box and the truck is 0.8. What is the maximum forward force that the truck can accelerate with before the box begins to slip in the bed of the truck? Now, to help me kind of understand this problem, I might draw it as two boxes, right? Where the 400 kilogram box is A and the truck is B. And then I'll say MA equals 400 kilograms, MB equals 2,000 kilograms. Okay, so what's going on here? Well, basically, we're thinking about some external force that's being applied to B that causes it to accelerate to the right. Now, A is not going to experience that force. Instead, A is going to experience a static friction force because the box is stuck to the bed of the truck. Now, that static friction force is also experienced by B, so it would be going in the opposite direction because those are an action-reaction pair. And, of course, we've got the weight and the normal force for each object, but let's just sort of stick with this picture right here so that we can kind of answer the problem quickly. The key to this problem is thinking about the static force of friction that's causing the 400 kilogram box to accelerate with the truck. Basically, we're asked what is the maximum forward force that the truck can accelerate with before the box begins to slip. So this phrase right here, before the box begins to slip, that means that we need to consider Fs max, the maximum static force of friction that occurs. And of course, Fs max is equal to the coefficient of static friction times the normal force. And in this problem, we know that because this isn't on an elevator or anything like that, the normal force is equal to the weight of the box. So mu s times mg, but we have to be careful and write mag so we don't confuse the different masses. Okay, so that's how we figure out what Fs max is with the coefficient of friction 0.8. What do I do with that? Well, I know that on this top block, friction is the only unbalanced force causing the block to accelerate, so we can call it the net force on A. And I know that the net force on A is equal to the mass of A times its acceleration. So basically, I'm going to set Fs max equal to the net force. And so we'll write mu s mag is equal to MAA. And of course, it turns out we don't even need to know the mass of the box to figure out its acceleration because the mass cancels out. All I need to find the acceleration is the coefficient of friction and g, the acceleration due to gravity, or the gravitational field strength. So let's figure out the acceleration. 0.8 times 10 meters per second squared. So 8. 8 meters per second squared is the acceleration, the acceleration of the 400 kilogram box. Now, not only is it the acceleration of the 400 kilogram box, it's the acceleration of the box and the truck. They are both going to have that acceleration of 8 meters per second squared. Okay, so now let's stop thinking about the box individually, and let's not even think about box B. Instead, let's think about both objects and pretend like we're looking at one object being accelerated by that applied force. Okay, well, so now I know the acceleration of this, both objects is 8 meters per second squared. And in this problem, we know that this force, the maximum force, is what we're looking for. It's going to depend on that acceleration. So this is the net force. And we can set it equal to the mass of both objects times that acceleration. So the applied force F is equal to the mass, and specifically the mass of both, so ma plus mb, times that acceleration. Or, let's see, 400 plus 2,000, so 2,400 kilograms, times 8 meters per second squared. It's a big number. 19,000 200 newtons. So that is the maximum force that can be applied by the truck to accelerate the box before the box begins to slip. Now, again, to remind you what we did, we calculated what the maximum static friction was, and then we said, all right, what acceleration would we have if that was the maximum static friction? And then we applied that acceleration to both the truck and the box to figure out what would that overall force need to be. So 19,200 newtons. Now let's change this problem up slightly. A 400 kilogram box is on the back of a 2,000 kilogram truck. The coefficient of static friction between the box and the truck is 0.8. But now we're asked, what horizontal force does the 400 kilogram box put on the truck if the applied force of the truck is 16,000 newtons? So first of all, sometimes physics is just super confusing, and we ask questions this way because we, forget that we're human. The horizontal force that the 400 kilogram box puts on the truck is friction. And again, this could be static, it could be kinetic. Let's just call it friction. And we'll talk about if it would be static, if it would be kinetic, what we think. So this friction generally is going to be equal to mu times normal force. We'll look at that later. But basically, this problem is a little bit different. Instead of using the static coefficient of friction, we're actually going to think, well, let's start here. Let's pretend like we have both objects, A plus B, being accelerated by this force of 16,000 newtons. Well, the first thing that we should do is think, what's the acceleration? Right? The acceleration will be that net force over the total mass, and the net force is 16,000 newtons, and the total mass would be MA and MB, so 2,400 kilograms. So right off the bat, I'm going to figure out what is the acceleration with that 16,000 newtons. So 16,000 divided by 2,400 gives me 6.666 meters per second squared. A little creepy. Okay, so I know that that's the acceleration. I'm going to write it up here, 6.6 repeating meters per second squared. So what do I do with that? Well, now if I think about both blocks, right, if I kind of do the box on the box, or block on block, whatever. So now I've got this new thing where, okay, so that force really is being applied to B, and there is a friction force that's acting back, which is the friction force that's causing A to accelerate forward. So now when I focus in on A, I know that friction is the net force on A, and I can set it equal to the mass of A times the acceleration. So the friction, which is this, the horizontal force that it puts on the truck, that's what we're trying to find. I know the friction in this case is going to be equal to the mass of A times that acceleration. So I take the mass of A, 400 kilograms, and I multiply by the acceleration, 6.6 meters per second squared. And what I get is a number 2,666.64, or I think it's just 6 forever. Who knows? Anyway, so the idea is that this force of friction, yeah, it is. It's just repeating. There we go. This is the force of friction that exists between the box and the truck. And the reason, this would be static friction. The reason why we had to find the force of friction this way was because if we instead used that coefficient of friction, mu s, times the normal force, what we would be finding is the maximum static friction. And if I calculate that real quick, mu s is 0.8. The normal force of the box is 400 kilograms times 10 meters per second squared. So 0.8 times 4,000, 4,000 is 3,200 newtons. So here's why we couldn't use this equation to solve our problem. The acceleration of the truck from this 16,000 2,000 Newton applied force is not enough to actually reach the maximum static friction. 2,666 newtons is less than the maximum. So you could have calculated the maximum, but that would have kind of been the wrong idea. Instead, in this problem, you would want to consider, well, what's the acceleration if I multiply that by the mass of the block? That is going to be the answer to the problem, and it happens to be that this is the static force of friction, and it's less than the maximum. Moving right along. A 4 kilogram box is on top of a 6 kilogram box that is placed on a frictionless surface. A 10 Newton force is applied to the top of the box, so that's this applied force. What is the minimum coefficient of friction between the two boxes needed to keep them moving together? So, first of all, let's point out where there is friction and there isn't friction. There is no friction between the 6 kilogram block and the table, but there is friction between the 4 and the 6 kilogram blocks. So what I would probably do is call one of these things A and the other B, then write MA equals 4 kilograms at the top, MB equals 6 kilograms. And then I might just go ahead and draw some free body diagrams. And I'm going to do that on their own little dots real quick, just because I've already kind of cluttered up my picture. So A has that applied force F of 10 newtons, and then there's going to be the weight force down, Ma times G, its normal force up, which I'll call that NA. And then there's going to be a little bit of friction, which in this case is actually going to be to the left, because as this 4 kilogram box is moving to the right, basically the 6 kilogram box is going to drag back on it a little bit. So I'm just going to call this friction because there's only one source of friction in the problem. Okay, so that's A. Now let's think about B. B has a weight force down, MBG, normal force up, which we can call NB. And so now we think about what is actually causing the 6 kilogram box to accelerate to the right or to move together with that top box. Well, it's the opposite of this force of friction. This is a third law action-reaction pair. So basically, it's the 4 kilogram block is like dragging the 6 kilogram block forward, and the force that is doing that is a force of friction. Yeah, it's pretty straightforward. Okay, so what do we do for this problem? How do we go about solving it? There are a lot of different ways that we could solve this. Probably the fastest is to recognize that if I treat both blocks as one object, then there's no friction, an applied force of 10 newtons, so that's the net force. And I can find the acceleration by taking the net force and dividing by the total mass. So that 10 newtons, and then I divide by the total mass of 10 kilograms, which gives me an acceleration of 1. Okay, so they keep them moving together. That means they both are going to have the same acceleration, 1 meter per second squared. Okay, where do I go from there? Well, now that I know the acceleration of both, I can just focus in on B, the bottom block, and think, well, that friction force is going to be the net force acting on the box. Okay, so the net force on B is that friction force. Remember that the friction force is going to be mu times the normal force, and of course in this case it's going to be static. It doesn't say coefficient of static friction here, but it is implied that that's static friction because they're stuck together. And to figure it out, all I need to do is say, okay, mu s times the normal force, specifically on B, which is mbg. Okay, so now I know that this is the net force, and remember the net force is always equal to the mass of the object times the acceleration. So just kind of like in the last problem, I can say friction equals the mass of B times the acceleration, or mu s mbg equals the mass of b times its acceleration. Now, fun fact, I don't actually care about the mass of b for this problem. I can get rid of it. And now I know that the acceleration is equal to the coefficient of static friction times g. But in this problem, I know the acceleration. I want to find the coefficient of friction. So I take the acceleration and divide it by g. And in this case, I get the coefficient of friction is a ratio of acceleration experienced by the block, 1 meter per second squared, over the acceleration due to gravity, or 10 meters per second squared. And that would be 0.1. Right? Calculator says yes, yes. 0.1. So that is the coefficient of friction between the two blocks. All right, last box-on-a-box problem. A block M1 is on top of block M2 as shown below. M1 is 5 kilograms and M2 is 15 kilograms. Block M1 is attached to the wall with a rope. Block M2 is being pulled by a truck. The coefficient of static friction between the blocks is 0.4. There is no friction between M2 and the ground. Okay, so first of all, just like the last one, yes, friction between the two blocks. No friction between M2 and the ground. Very helpful. It really unclutters our problem. And they told us that the coefficient of static friction between the blocks is 0.4. I'll write that down. Mu(s) equals 0.4. Okay, and we're asked to find the maximum tension in either rope before M2 begins to move. Okay, so what does that mean? Well, that means that we're going to be dealing with Fsmax. It's asking what will the tension in the rope be when Fsmax, the maximum static friction between the two blocks, has been reached. And remember that we calculate Fsmax, the maximum static friction, with the coefficient of friction times the normal force. Now, real quick, let's draw a free body diagram so we can sort of keep track of these things. 1, we say 1 instead of A, is M1G, and then there's a normal force up. We'll call that N1. And then there's tension here in the rope, so we'll call this T1. And then, of course, this friction between the two, this is going to be causing M1. There's a force of friction kind of bringing M1 to the right. So we would call that the force of friction. And I don't need to say F1 because there's only friction here. There's no friction on the ground, so we'll just call that F. Oh, and Fsmax, because we know it's the maximum static friction. Okay, so 2 is going to have M2, G down, and the normal force 2 going up. And remember, the normal force and the weights, they're equal in these problems. We don't really need to use them too much in this, just to find the maximum static friction. And then there's going to be tension in this rope right here. Now, because this is a second rope, I'm going to call this T2. And then there will, of course, be the friction between these two blocks, which as M2 goes to the right, it's going to be experiencing a force of friction pushing back on it, like M1 is sort of holding M2 back as it tries to move right. Now, that is the same force of static friction that's between the two blocks. Remember, it's a shared action-reaction pair. Okay, so a lot of stuff I could do in this problem. I could write a system of equations, but there's something really key, really important to this problem that we have to see in order to quickly solve it. And that is simply this. They're not moving. They're stuck together and they're not moving. That means that they are not accelerating. Their acceleration is 0. Now, this could also be true if somehow these boxes were moving with a constant velocity. Like maybe, oh, I don't know, this is like some separate box and it's moving with them. Oh, weird. Maybe that third box is moving with them or something. I don't know. And they're moving with a constant velocity. Either way, they're at rest relative to each other. There's no acceleration. That means that the forces on each object are balanced. Okay, so that means T1 equals F's max, if I look at the free body diagram on 1, and F's max equals T2. Okay, so first of all, this tells us that the tensions are equal. And the other thing that we need to do is, in order to figure out their magnitude, we just have to calculate F's max. So F's max is the coefficient of static friction times the normal force, but in this case, we're using the normal force of M1. So mu s times M1g, or 0.4 times 5 kilograms times 10 meters per second squared. 0.4 times 5 times 10 is 20 newtons. Okay, so that means T1 is 20 newtons, and so is T2. And you have finished this kind of confusing problem. Okay, so I know that this can all be a lot, but our basic procedure is to write down information that we're given, right, and unknown things, think about what we're trying to find, and then to draw free body diagrams, and use those free body diagrams to come up with equations that might help us. We're going to keep doing that. It's more of like a method than it is a particular solution. You can use it in all kinds of different situations. Okay, you did a great job. You're so smart. This video is over.